Hello everyone. Today we are going to see about microwave filters. So you might have studied about the microwave filters and in general and circuit theory, but here we are going to discuss about the filters, how they are designed, how can we realize it at microwave frequencies. So let us start with the filters. Basically, a low pass filter, high pass filter, band pass filter, and band reject filters are the four different types of filters, and also one more filter, all pass filter. Alright, so here low pass filter which passes low frequencies, and high pass filter passes higher frequencies. Band pass filter passes particular band of frequencies. Band reject filter which actually rejects a certain band. So in fact it is also known as a band stop filter. Sometimes you may think about this band pass filter, band stop filter as a notch filter or band reject filter. Okay, so now we have another filter, all pass filter. This will can be designed in at microwave frequencies because the reason is all pass filters are designed for providing a phase delay, but at microwave frequency we can provide the phase delay by a simple line length. For example, if you want to design a 90-degree phase delay at frequency of, let us consider 1 gigahertz. So at 1 gigahertz wavelength, that is 30 centimeter. So lambda by 4 will be 7.5 centimeter. That will provide 90-degree phase difference. But when you want to design the same thing at 1 megahertz, then this 1 megahertz wavelength, corresponding wavelength will be 300 meter, and therefore lambda by 4 will be 75 meter, and you do not want to have PCB with 75 meter length. Okay, so that's why all pass filters are designed at lower frequency but never ever at microwave frequency. So here let us discuss about the filters at microwave frequencies, which are nothing but based on the transmission line concept, because here inductors and capacitors are actually they are not present. They are realized by using transmission line concept. So when we come to this transmission line concept used in the design of filters at microwave frequency, we must one thing we must understand, the transmission line which is shorted at the end, which behaves like an inductor, and a transmission line which is open circuited at the end, which behaves like a capacitor. So the same concept is used to realize the low pass filter by using these transmission lines, and hence you don't have to see any inductor and capacitor in there. Right. So first let us look at the amplitude responses of ideal filters. So here ideal low pass filter frequency response, which will pass all the frequencies up to omega c, and then it will not pass above the frequencies above omega c. Now similarly the high pass filter, ideal high pass filter, which passes the frequencies above omega c and below omega c are not passed by it. Okay, similarly band pass filter and band reject filter. Band pass filter will pass the frequencies between omega c1 to omega c2 without any attenuation, and it will provide complete attenuation at the outside this range. Similarly, band reject filter or band stop filter or notch filter, which provide attenuation for this band of frequencies omega c1 to omega c2, and it passes all the other frequencies. Okay, so if you look at this from low pass filter, we can see that the transformation is very simple. So if you just make S in the S domain, the filters, if you want to analyze the filters in the S domain, S can be is equal to j omega for a low pass filter. Then for the high pass filter, just if you replace S by 1 by S, then it represents the high pass filter. Okay, so now band pass filter and band reject filter will also be just opposite to each other when you design. Right. First, let us start with the very simple low pass filter. So this is not the circuit which is used at microwave frequencies. So here we have considered RC circuit. RC circuit is nothing but a first order low pass filter. So here it is also known as integrator. Now to find the transfer function of this RC filter, H of S, it is very simple. It is a ratio of V2 of S by V1 of S. This is the output voltage divided by the input voltage. So we can find this ratio in terms of the impedance ratio also, because it is similar to the impedance ratio. So the impedance at the output is only because of the capacitance, that is 1 by SC, and divided by the total impedance, which is looked at the input side, which is the sum of the impedance given by resistance R and the impedance given by the capacitance. So here 1 by R plus AC. So when you multiply this by S and divide by R, then you will get 1 by RC in the numerator and S plus 1 by RC in the denominator. So H of S will be 1 by RC divided by S plus 1 by RC. Where here the omega C, the cutoff frequency, which is equal to 1 by RC. Okay, so here we can actually use the normalized frequency, because we need to deal with the normalized frequency, then only we can design any the filter at any desired frequency. So the normalization can be done by assuming omega c is equal to 1. Then we use the frequency transformation to design the desired low pass filter at any other frequency. So here omega c is equal to 1 means 1 by RC is also equal to 1. So when you substitute 1 by RC equal to 1 in the H of S equation, you will get 1 divided by 1 S plus 1. Okay, so here from this transfer function, you can find out whether this transfer function represents a low pass filter, high pass filter, or band pass filter. This can be done by quickly checking by substituting the value of S as 0. When you substitute S is equal to 0, this h of s will become 1. So, and when you substitute s equal to infinity, this h of s will become 0. So, this is which indicates that for low frequency it passes, whereas for high frequency the output response of the filter is 0. Therefore, it is like a low pass filter. So, from the transfer function itself, we can easily understand what type of filter is this. And when you substitute s is equal to j omega, actually s is equal to sigma plus j omega, is it not? So, here we assume that the lossless situation, and therefore the attenuation factor is 0, sigma is 0, and therefore s is equal to j omega. So, when you substitute s is equal to j omega in the expression h of s, h of j omega is equal to 1 divided by 1 plus j omega. So, magnitude of it is equal to 1 by root of 1 plus omega square. So, this is the transfer function of magnitude response of the first order low pass filter. Whereas for nth order filter, it will be 1 divided by root of 1 plus omega power 2n, where n is the order of the filter. Now, if you plot the response of this filter with respect to frequency and the two at microwave frequencies, we are going to represent these things in terms of S parameter. The variations are the response of the filter in terms of S parameters. So the transfer function from here to here, from h of j omega with respect to omega, that is denoted by S21, which is the transfer function, which is similar to the low pass filter frequency response. And the next one is S11, which is the reflection coefficient, and here the omega c is the cutoff frequency. So the ideal frequency response, and then the transfer function S21, and then S11. All are plotted here with respect to the omega, and here in terms of dB, the maximum value will be 0 dB, or the amplitude will be equal to 1. And from that, the 3 dB minus 3 dB line, if you plot, then it will pass through the point at which the S11 and S21 cross each other. So that is the point corresponding to the cutoff frequency. Okay, but at microwave frequency, we usually we cannot use the resistors in the filter, because the resistors will have high loss in the high dissipation when the frequency increases, and therefore these resistors are replaced by the inductors at microwave frequencies, because the dissipation is less for the inductance when compared to the resistance at microwave frequencies. So let us first look into the realization of the filter, low pass filter with the lumped elements, and then we'll see how these filters are designed at microwave frequencies. So for that, let us draw the lumped element realization of low pass filter, so which consists of inductor and capacitors. Okay, and here there are two configurations I have drawn. First configuration, in which the source is the voltage source, so in which the resistance source impedance is in series it is connected, whereas the second one is current source, which is having current source, therefore the resistance, the source impedance is connected in parallel. Okay, and one more difference between these two configurations is, in the first configuration, the first element is capacitor, and then inductor, and then capacitor. So in that pi network, similar to the pi network, the elements are connected, whereas in the second configuration, first element is inductor, and then capacitor, and then inductor. So here T network is used for making this configuration. So in both the cases, we can design the filter. So either case, the response will be same. So any configuration can be used for finding out the for designing the filter. Okay, so it doesn't matter, any configuration can be used. Any element can be considered as the first element, either T network or pi network can be used. Okay, so now to find out the response of this and to design this filter, let us consider the h of j omega. So here h of j omega is, for the nth order filter, it is 1 divided by root of 1 plus omega power 2n. Okay, so here when you plot this response with respect to frequency, when you vary this attenuation, when you plot this, here we can see different responses for different transfer functions h of j omega. So here there are three different variations are there. One is Butterworth variations, that is maximally flat frequency response, that is called as Butterworth filter frequency response, because it was proposed by Butterworth. And another one is Chebyshev filter, and then the third one is linear phase filter. Okay, so here already I have studied about the Butterworth, Chebyshev and linear phase filters. You can classify those filters into two categories of finite impulse response filter and infinite impulse response filter. Here, this advantage of the filter is flat frequency response, whereas the disadvantage of the Butterworth filter is the transition band width is very large when compared to Chebyshev filter. It's very slowly moves from the passband to slow band. That is the disadvantage. Whereas the another filter, Chebyshev filter frequency response, which is also called as equiripple filter, the advantage of this equiripple filter is quick transition from the passband to stop band. So transition bandwidth is very less when compared to the Butterworth filter. But the disadvantages, the ripples are exist in the passband as well as stop band. So based on the existence of the ripples, you can classify the Chebyshev filter into two types, type 1 and type 2. If the ripples are present in pass band, it is called as type 1 filter, whereas if the ripples present in the stop band filter, it is type 2 filter. Okay, then the third one is FAR filter, which has linear phase response, so which has maximally flat response as well as linear phase response. Okay, so now let us look into the design of maximally flat Butterworth low pass filter design. For that, we know that the h of j omega magnitude the whole squared is equal to 1 plus omega by omega c the whole power 2n the whole power 1 minus 1. Actually, you will write this in the DSP, digital signal processing subject 1 divided by 1 plus omega by omega c the whole power 2n, or square root of omega by omega c the whole power n. Actually, omega c is the cutoff frequency, which is equal to 2 pi fc. Okay, and in order to design the filter, first we need to calculate the order of the filter. So the expression for the order of the filter is log of 10 to the power a divided by 10 minus 1 divided by 2 into log of omega 1 by omega c. What is a here? A is the attenuation at the corresponding frequency omega 1. Okay, so attenuation which is required at the frequency omega 1. Based on that, we need to design the filter. So here the order of the filter, which depends on the attenuation which is to be produced at a particular frequency. Okay, and it also based on the cutoff frequency. So here from the order of the filter, we can design the parameters of the filter, because we have defined the elements of the filter in terms of the parameter G0, G1, G2 in the previous diagram, right? The C1 is denoted by G1 and L2 is G2 and C3 equal to G3 and the last Gn plus 1. Similarly, in the next configuration also. So the parameters, the components of the filters are based on, are defined with the G parameters. So here G0 to Gn plus 1 we need to determine. So the parameters G0 and Gn plus 1, which are nothing but the source impedance and the load impedance, and we consider that the impedances are normalized impedances. Therefore, G0 and Gn plus 1 are equal to 1. So here Gk in general, which can be expressed as 2 into sine of 2k minus 1 into pi divided by 2n, where k is equal to 1, 2, 3, etc. n. Okay, so using these equation, we can determine the filter components, right? Filter components, inductors and capacitors can be designed. So for example, if you have n is equal to 5, order of the filter is 5, then G0 and G6, Gn plus 1, which are equal to 1, and the remaining parameters have to be determined. So G1 is equal to 2 into sine of 2k minus 1. So here k is equal to 1, so 2 into 1, so 2 minus 1 into pi divided by 2 into 5. Okay, so here 2 sine of pi divided by 10, whose value is 0.618. Similarly, you can determine G2, G3, G4, G5, and when you write all these values, look at the relationship between the values. Here the values or G parameters are symmetrical about the center value G3. So here G2 and G4 are equal, and G1 and G5 are equal, and G0 and G6 are equal. So it is possible, or it is sufficient to calculate only half of the parameters, and the remaining parameters can be determined easily from the other values. Okay, so now let us compare this. Before that, since we have G parameters for the normalized impedances, so here normalized impedance means R value equal to 1, and we assume that omega C is equal to 1, that is omega equal to 1. Therefore, we need to do impedance scaling and frequency scaling for the components. So we need to change all the components by the same impedance factor. So let us consider the same impedance factor as R naught, right? And therefore, the new impedance will be calculated based on this impedance factor. So here, actually the impedance of the inductor is Z is equal to J omega L, where the L dash new value of the inductance will be equal to R naught into L, because it is to be increased. If you want to increase the value of the inductance, it is to be multiplied by because the value of it is to be multiplied by the factor R naught, so that the original value of L should be modified by the factor R naught. So the impedance increases. Okay, the next value of L is to be calculated by means of multiplying the previous value of L by R naught. Okay, similarly for the capacitance, we know that the capacitance impedance is given by 1 by J omega C. Here, to increase the value of impedance, we have to decrease the value of the capacitance. So the capacitance should be decreased by the factor of R naught. So there are the new values. This is called as impedance scaling. New value of C dash is equal to C divided by R naught. Okay, so here C is the previous value of the capacitance, and it is to be decreased by this value. Okay, so that it can be increased. The value of the capacitance can be the value of the impedance can be increased. Right. This is what impedance scaling. Okay, whereas frequency scaling is frequency scaling. For that we need to do the impedance. We need to keep the impedance value same. We need to change only the frequency value. Okay, so for example, again, what is impedance of the inductor? Z is equal to J omega L. Now since omega is has to be increased, we have to decrease the value of 1 by the same factor omega C. We have to decrease the value of 1 by omega C, 1 by the same factor omega C. Similarly, the impedance for the capacitance is 1 by J omega C. So in order to keep the impedance same, the frequency is increased by decreasing the value of the capacitance. Okay, so ck dash is equal to ck divided by omega c. So when you combine these impedance scaling and the frequency scaling, lk dash will be equal to r naught into lk divided by omega c, and ck dash is equal to ck divided by r naught into omega c. Okay, so this is what the frequency scaling as well as impedance scaling. So after doing this impedance scaling and frequency scaling, you can use these inductance values and capacitance value for designing the filters. Okay. So let us solve this, let us understand this theory by solving a problem. So here, this is the problem given. Calculate L and C values for a maximally flat LPF, low pass filter that has a 3 dB bandwidth of 400 MHz and attenuation of 20 dB at 1 GHz. The filter is to be connected to 50 ohm source and load impedances. 50 ohm source and load impedances. So first we need to determine the order of the filter N, which is equal to log of 10 to the power A divided by 10 minus 1 divided by 2 into log of omega 1 by omega c. Substitute the values of attenuation omega 1, omega c. Here in the problem it is given that attenuation is 20 dB at 1 GHz. Okay, so A is 20 dB and omega 1 is 1 GHz. So log of 10 to the power 20 divided by 10 minus 1 divided by 2 into log of, here omega 1 is 1 GHz and omega c is 400 MHz. So 1000 by 100, 400 we can represent it by 1000 by 400. So value of this N becomes 2.51. Okay, but we cannot have the order of the filter as 2.51, so we need to have the integer value as 3. So N, the order of the filter is 3. Now we need to calculate the G parameters. So here we know that the source impedance and the load impedance, since we are using normalized impedances G0 and Gn plus 1, 3 plus 1, G4 is equal to 1. And then we need to determine the other parameters G1, G2, G3 using the expression 2 into sin of 2k minus 1 into pi divided by 2n. So using that expression, we can determine the values of G1, G2, G3 as 1, 2, 1. Okay, so here look at the values, it has the symmetrical property. Okay, so 1, 2, 1, 1, 1, 2, 1, 1 are the G parameters. So using these parameters, we can determine the values of inductors and the capacitors which are used for designing the low pass filter. Here we have taken the first component as inductor, second capacitor, and then third inductor. We can also design with the first component as capacitor, inductor, and then capacitor, but just look into this design now. So first component is L1. L1 is equal to Z0 into G1 is the previous one, right? Previous inductor value divided by omega c. So for both impedance scaling multiplied by Z0. Here instead of R0 we have used Z0. So Z0 multiplied by G1 divided by omega c. Both impedance scaling as well as frequency scaling is done. So here the value of this Z0 is 50 ohms and G1 is equal to 1 and divided by omega c is equal to 2 pi into FC. FC value is 400 megahertz, so 400 into 10 to the power 6. So the value will be 19.9 nanohenries. Okay, and here L3 is also equal to L1, right? L3 is also equal to L1 because Z0 into G3 divided by omega c. So here G3 is also equal to 1, therefore L3 is also equal to 1, which is equal to 19.9 nanohenries. Okay, but C2, which is equal to G2 divided by Z0 into omega c. Okay, so the value of G2 is 2 divided by Z0 is equal to 50 into 2 pi into omega c. So 400 into 10 power 6. So here 10 to the power 6. So which is equal to 15.9 picofarad. Okay, picofarad. So these are the values. So let us design the circuit with a source, voltage source, and the impedance, input impedance 50 ohms. And then the inductor, first inductor 19.9 nanohenries, and then capacitor value is 15.9 picofarad, and the next component is inductor. This is also 19.9 nanohenries, and the output impedance is 50 ohms again. So which are connected here, right? So this is the actual circuit which will meet the requirements of the 400 megahertz cutoff frequency and at least 20 dB attenuation at 1 gigahertz. Okay, now let us see the response of this particular filter. So we'll simulate this filter by giving input and by operate this filter with the various frequencies. So the output of the simulation of this third order Butterworth low pass filter is like this. Okay, simulation output of third order Butterworth low pass filter, right? Butterworth low pass filter. Here look at this response. It is like this, and here both are in the same line, right? So 0 dB, this is attenuation in dB, and here frequency in gigahertz. So it starts from 0.0 and then 0.5, okay, and 0.5 and then 1 gigahertz. Here 1 gigahertz and then 1.5 till 2.0. Here this curve corresponds to the transfer function S21. This is S11 reflection coefficient. Here the response S21, which is a low pass filter response, right? Similar to the low pass filter response, whereas the S11 is the reflection coefficient. Okay, so here we have designed this filter for the cutoff frequency of 400 megahertz, that is equivalent to 0.4 gigahertz. So it cut off at 0.4 gigahertz, right? It's cut off at 0.4 gigahertz. So this must be corresponding to 0.4. Okay, this line. So here this is corresponding to 3 dB, right? So the S11 and S21 both meets at the point which corresponds to 3 dB minus 3 dB from the maximum value, right? And this circuit consists of only inductors and capacitors. So there is no insertion loss in this particular filter. So this is an ideal response. Practically inductors and capacitors will have some losses. Right, the response will not be exactly equal to 0 dB, like 0 dB, but it may be in 0.1 dB, 0.2 dB, like that, because of the losses which is included by the inductor and capacitor in practice. So now let us see what is the response at 1 gigahertz. At 1 gigahertz, this is corresponding to 24 dB attenuation, but we designed the filter for 20 dB attenuation at 1 gigahertz. Okay, but here what we obtained is 24 dB attenuation at 1 gigahertz. Even though it is acceptable, this 24 dB deviation from 20 dB, it is because of the variation in the order of the filter, because actual order of the filter what we obtained is 2.5, but we rounded off it to n is equal to 3, right? So because of this variation in the order of the filter, third order filter, we get the attenuation 24 dB instead of 20 dB. Okay, so we cannot get the exact 20 dB attenuation in the at the required frequency. Okay, so this is because of the change in the order of the filter, and if you vary the order of the filter, then the attenuation will also be different, right? If you increase the order of the filter, then the attenuation will be high, increased to 30 dB or 35 dB. The attenuation, when it is high when compared to the given required attenuation, it is acceptable only. So this is about the design of the low pass filter, Butterworth filter. Alternate design is also possible with the starting component as capacitor and then inductor and then capacitor. This response is similar to the same response, so we can obtain this with the design. Okay, so with this I'll stop the design of the Butterworth low pass filter.